Okay, so it's already the time. So welcome to the next lecture from Effective Software. Today I will focus on object allocation, how it internally works in Java Virtual Machine. Then I will talk about Bloom filters. What are these data structures? What are they good for? And at the end, I will talk about references and effective caching inside Java Virtual Machine. So let's start with the object allocation. I've already mentioned during my courses several times TLAB, which stands for Thread Local Allocation Buffers. That means that each thread has its own dedicated exclusive area in the hidden space, and this area is moreover aligned with the NUMA, which stands for non-uniform memory access. If you have multiprocessor systems, every processor, because the memory controller is inside CPU nowadays, every memory is connected to particular processor. And then there is a different speed of accessing data in the memory which is connected to that processor, or in the memory which is connected to different processor. So in this case, if the thread where the object is allocated is running on some particular processor, that thread allocation buffer is created in the memory which is local to that processor. That is this alignment with the NUMA. This approach with the thread local allocation buffer removes some bottlenecks. There is no need for synchronization if there are multiple threads running in your application and they are creating new objects, because each thread has own dedicated part of the memory for allocation of new objects. Moreover, it removes fault sharing from the cache perspective, because thread allocation buffers are not only aligned with the NUMA architecture, but also with the cache line size. So the minimum size of the buffer is at least one cache line, but usually is much more bigger, and it starts and ends aligned with those cache line positions. So objects created by one thread are then inside single cache line, and there is no object for different thread in that cache line. For sure, after allocation, those objects can be accessed later by different threads after initialization of the objects, but that's up to the programmer to handle this situation and remove fault sharing bottlenecks. Allocation of an object inside this thread allocation buffer takes just few native instructions. Why? Because it's used the bump the pointer technique. There is a pointer for every thread pointing to the start of the empty space in that thread allocation buffer. So anytime there is a request to create new object, allocate new object, it simply increment that pointer by the object size, and the previous pointer position is simply the new address for that newly allocated object. That's very simple technique, and that's possible only if the buffer is always clean. If there is no more space, because it's finite, the size of the TLAB is finite, if there is no more space for allocation of the object, or the object is bigger than the TLAB, then synchronization across threads must happen inside that process. And that synchronization is usually based on atomic instruction, which are in case of CISC architecture, lock prefix instruction, for example, lock increment instruction. Inside Java Virtual Machine, there is an adaptive resizing mechanism for TLAB size. So if the thread is allocating a lot of objects, further TLAB sizes are increased. If there is less, they are decreased to some minimum. That's working well, unless some extreme cases, like, for example, thread pooling, where the allocation pressure can be really varying depending on the task which is running within the specific thread. because it's always linked, the next size is always linked to the thread itself. There also exists a couple of options which can be used for tuning TLAB sizes. Minimum, maximum, if you would like to debug that information, you can enable this debug, and so on. So let's look to the example. This structure object was introduced during last course. It's the object having a lot of fields inside with various types. In our case, I'm showing the code in AT&T syntax, which means you need to read this instruction from left to right. So the destination is on the right side every time. And this is C2, just-in-time compilation, C2 output. In the case that it's used standard OP, so the heap size larger than 32 gigabyte. So the structure object size is in this case 96 bytes. So how such allocation looks like if the code includes a new structure? Simply, here it reads that pointer for the bump the pointer technique into R11 register. R15 in every code in Java virtual machine is always pointing to the thread local data. So every thread running this has different R15, and within that thread data, there is information. There is some table in the beginning of that structure. In this case, 60 hexadecimal offset from that table is the pointer to the TLAB. So then it tries to increment that pointer, in this case in R10 register, increment by 60 hexadecimal, which is this 96 bytes decimal. And before it thinks, oh, object is allocated, it has to check whether we are already over the end of the region, which is here. This compare just checks the bound for the current TLAB buffer. If we are out of bound, this jump position calls internals of Java virtual machine to allocate new thread allocation buffer, plus also allocate that new object, because it every time knows from where that jump goes, so it knows what kind of object it is, etc. And if there is a space, we are just storing that pointer back. So you can observe that there is no synchronization needed, no atomic operation needed for this allocation, and that's it. At this moment, we have already position for this new object allocated. And that position is in R11. R10 was used as an end of that position. This prefetch instruction, I've already mentioned that once, prefetch the cache lines ahead. So it tries to speed up further or later allocations. It says to the processor, please prepare memory allocation and do not block execution of these commands, because it's asynchronous. This instruction is asynchronous, and processor tries to acquire cache line for that address. Then there is some preparation here for the object initial nulling, because every object in Java which is created is automatically contains 0, false, or null as a pointers. And then it's initialize the data structures according to the object header. So you can see that there should be this class reference, and that's exactly what you see here. This is pointer into R10 register to the internal representation of the structure object, and that R10 is saved here into the object header offset 8, which is exactly this position. To the mark word is stored here in this place. And in this space, this sequence of instruction nulls the object. The whole content, the data area, object data, are nulled here using this special instruction, which automatically, repeatedly clean up the memory. It's vector-based instruction, and it's extremely fast. So if we run this code with a lot of allocation of such object, I've already introduced this tool, Java Mission Control, last time, which contains this flight recording feature. and you can see information about TLABs. 65 TLABs was allocated in order to allocate million allocations of structure object. There was this dynamic sizing of TLAB size for every allocation, total memory, and you can also see the timeline here. There is no object which is not fitting that area. If we look to the details, the second tab here, you see, if you click to this, you see I've run some code which was class structure test, allocate method, or all this allocation came from this place of the code. And that's come almost free of charge. So this method of flight recording is very useful. It's not very precise because you just record information about objects which are allocated when there is no more space in TLAB buffer, but at least it gives you some insight what is happening dynamically in your application. So let's look to the example. Let's have simple example with method 1, which have array of arguments, array of strings as an input argument, and output is also array of strings. And in this case, we would like to filter, we are providing some words or sequences of words which can contain also digits. So what we would like to do, we would like to filter out from this provided inputs anything which contains any digit, so keep just alphabetical words there. Then we would like to order them, not considering the case, in reverse order, and return back ordered sequence without any words containing any digits. In this case, we are creating pretty nice code using streams. So out of that input array, there is created stream, which can run in parallel. Then there is applied filter mechanism using lambda function. In this case, it's runnable. It's not runnable because it has one argument. Calling matches, which is regular expression. This matches everything which doesn't contain any digits. If there is digit, it's filtered out. So it keeps in the further stream, it keeps only the values which doesn't contain any digits. Then we would like to sort that stream using the provided comparator, string and string, comparing two strings every time. And what we are comparing, here you can see the lower to lowercase. So we are not interested in case ordering, but case insensitive ordering. So everything is first converted to lowercase before comparison. And we are interested in reverse order of that list. Finally, we are collecting the remaining elements into list structure, which is finally converted into array with the adequate size. So that's pretty nice composition. But from runtime perspective, if you call this example with 40 input arguments, or not arguments, one argument with the array size 40, where 27 strings inside that provided array is without digit, and the remaining 13 contain some digits, and then run this example with the profiling of the memory allocation, you can see that this simple code, with just this 40 elements, implies almost 1,500 allocations of new objects, where the size of those objects is more than 100 kilobytes. That's crazy, because code looks that simple, but it shows, okay, there is a lot of allocation. So we are slowing down our performance of the application. We are also increasing the pressure to the garbage collection, which furthermore slow down execution of our application. Where there are so much allocation, there is a lot of things here. So just highlight some of them. For example, this matching of regular expression. it's constructed every time. So in fact, there are constructed 40 different regular expressions which needs to be compiled. That's one thing. So pattern compilation happens every time. The very same is applied to the sorting. The construction of this comparator is applied for every element, in this case 27 times. So and streaming mechanism itself also implies a lot of allocations. So what we can do to resolve this problem, we can simply rewrite this example into optimized thing. So in order to remove that frequent creation of comparator, we can create just static single comparator, just single instance, case insensitive order in reversed manner, and then rewrite the body of that method into this example. So let's allocate array for the output, and then for each of the input, first check whether it should be included or not based on the presence of the digit. So we can simply go iterate over all characters in every string, and if we are detect that there is some digit, something bigger or equal than 0 and also smaller than 9 in ASCII, we say, okay, filter out. And for those which are not filtered out, include that into the accumulator used for the output, which was created here. Then let's call the sort on that accumulated data, which are already filtered, using that comparator, which are created here. And finally, we are using copy of array to restrict number of elements, because initially we assume the worst case that there could be there is probably no word containing any digit, so we reserve the full length, but we would like to return only the length of the array which maps the really used position, which is done here. So if you look to this example with the exactly same input, 40 elements, 27 without digit, you can see there are just 2 allocations with very small size, just 300 bytes. Why 2? First allocation is here, the accumulator for the output, and second is here, because we need reduce. There could be a condition saying that if I is the size of the input, let's do not allocate anything. That could be also optimized. And execution of such code is much more faster than the other, and also does not create that huge pressure on the garbage collection itself. So you should know what you are using, what kind of libraries, like streams, regular expression patterns, comparators, because even simple code can easily be very inefficient. It can create a lot of small, short-lived objects. That's the better case if there are short-lived and small objects. Small because they fit TLAB, and short-lived because they die in the young generation. They are not promoted to old generation. You have to know, because not every allocation is bad if you look to the code, because you have to know whether escape analysis is applied and what is the result of that escape analysis. I will talk about escape analysis on the next slide in detail. I've already mentioned that objects in TLAB fulfill the data locality pattern, so that are then quickly accessible because multiple objects are in the same cache line. There are NUMA aligned. There is no fault sharing, that was already mentioned. But on the other hand, these small short-lived objects increase the pressure on the garbage collection. And also, if there is that huge pressure, it can easily happen that some other objects are, because of that pressure, promoted earlier to the old generation. So that cascadely you can increase not only minor garbage collection, but also major garbage collection. Even worst case is when you have a lot of long-lived objects, objects which survive minor garbage collection. Each time these objects during garbage collection there must be traversed, and it costs another time. Compaction of the memory must then copy a lot of objects, another further slowdown. And also promotion to the old generation somehow breaks the original data locality, because the objects which survive the minor garbage collection are copied somewhere to the old generation, and that original data locality can be broken already. And also promotion of the objects to the old generation can imply more frequent false sharing issue, that various cores are accessing the same cache line, not just for reading, but also for modification, and that extremely slows down the execution of the code in nowadays computers. So let's talk about escape analysis in detail. Escape analysis is an optimization technique which is applied in just-in-time compiler and only in C2 compilation, as introduced during my, I think, first course. So C1 compiler doesn't do this escape analysis at all. Moreover, escape analysis is performed on every new object allocation. So every attempt to create new object is considered. And it happens after inlining of all hot methods. That's crucial. After inlining of everything inside, then escape analysis is done. You will see why. Every escape analysis can then be classified, every new object creation can be then classified into one of these three cases. So let's go through them. No escape case means newly created object does not escape that method where it was created at all. All usages, even if that reference to that object is passed to another method, those methods are inlined. So every usage is inlined. That reference is never assigned to any static variable, because that then means it cannot be classified as no escape, or object fields. It is just stored in some local variables. If it is array, any indexing to that array must be from the just-in-time compilation perspective constant. So cannot be anything which is modified every time. So if you have for each, then it's work fine because it's constant. But if you are randomly accessing elements based on some other input to that method, then it's not working. So what happens if that new object allocation is classified as no escape? For no escape objects, there is no allocation of object at all. What is there is that the just-in-time compiler performs something which is called as a scalar replacement of the object. So in our case of the structure object, instead of allocating new objects, which is 96 bytes long, let's consider every field of that object simply as new local variable, and that's it. So it's replaced the content of the object with dynamically created local variables. And those local variables are at most allocated inside stack instead of inside of heap. So if they are allocated inside of stack, they automatically disappear at the end of the method when the frame from the stack is removed. That's a very big benefit. Moreover, in many cases, if that object is not that big, or we are not using all fields, those local variables from the stacks are mapped to the register, and maybe there is even no space allocated at all, because simply those fields are mapped to the registers, used as the registers. Nothing is in the frame, and frame size is not affected at all. So the effect is that there is no garbage collection impact at all. And we do not track the references to those objects, because simply there is no reference at all if the object is not created. So that's very beneficial optimization technique. So anytime if this is possible, object is not allocated. The other classification of new object allocation inside escape analysis is argument escape, arg escape. This is the case when the object is passed as a reference, or a reference from some different method which is not inlined. So it simply escapes the context of this method as an argument to some different method. In such case, we cannot do that scalar replacement, because other method doesn't know anything about that composition of the object and mapping to some local variables. Instead of that, object needs to be created, but still there is some optimization technique which can occur, and that is that there is all monitors. Monitors is thing used for the synchronization, for the critical sections, are automatically eliminated, because that object is created inside that thread, and for sure it is used as a data inside other method by this thread. So if there is any synchronize on this object which was just created, we don't need perform that synchronization at all. So it still speed ups the execution, but object needs to be allocated on the heap in order to be used somewhere else. And the last classification case is global escape. That means nothing which was mentioned before is applicable. So we need create the standard object, and we cannot eliminate any synchronization or any monitors. So let's look to further example. Here we have a vector class which contains two fields, 1 and 2. Both are final. So from the perspective of patterns, this is immutable object. So anytime you would like to modify any element of that vector, you need create new vector in the constructor and assign values. So there are provided some methods, for example, sum two vectors together. So the result cannot be modification, it must be creation of new vector. Scalar multiplication, same thing. Scalar multiplication results into single number, so we need access the components, multiply and sum them together, and that's it, return that number. And also there are provided some getters, because we are defining our fields as a private. Could be public, then getters are not needed. And then let's define this compute method. That method is designed just for the demonstration purposes. So let's define our compute method receiving one input argument, outputting one output. Internally, it's first create vector using that input argument. First element of that vector is simply increment by 1 of that input. Second is multiply by 2. Then there is also, for demonstration purposes, synchronization on that vector. And finally, we are summing that vector with the same vector and compute scalar multiplication with that, again, same vector, which results into single number, which should be output of this method. So let's look how such native code looks like after just-in-time compilation of C2 compiler. Here you can see that it's a result of compilation of compute method, which includes, this is the trace, you can see there are included inlined a lot of hot methods, including constructor of the vector, constructor of the object, addition, getters, everything is included or inlined. So here we have our compute. So it inlines all these usages together and then performs escape analysis and found, is this new allocation here and also allocation inside addition? Are there, every of that allocation is analyzed and it found, okay, it's no escape category. And here is on the left side, you can see the resulting code. So here we have initially some method prologue, allocation of the frame. Here we have method epilogue, removal of the frame, and also in case of Java, there is this test for the save point. And this middle part is the body, and you can see that there are only movement, addition, and bit rotation operations, and multiplication is needed as well, nothing else. So no allocation of the object at all, and the computation is even furthermore optimized. You can see that multiple registers are used. That is used because, as I mentioned, our current superscalar architecture of modern CPU allows execution of multiple instructions in parallel if they are not depending on the same registers. That's exactly the case here. So the execution is just a couple of clock cycles because various intermediary results are computed in parallel and finally combined into resulting value here. So you can see there is no allocation, no synchronization needed in case of no argument escape. So what is the takeaway from this example? Not every object in the source code is bad. If that object is used wisely, it can be eliminated within the compilation. So you don't need to take care about any optimization of that object at all. Because usually every optimization makes the quality of the code for the reading worse. The code is more complex, it's unreadable, and it's more probable that the developer which will make some changes later will introduce more bugs then. So in this case, optimization of this relatively clean code using immutable object is not needed at all. So let's move to the next block inside this lecture, and that's related to the Bloom filters. Bloom filter is a special data structure which is, first of all, it is probabilistic data structure. It was developed by a man who is called Bloom in 1970. So pretty old data structure. It was mathematical. And that data structure allows these two operations. The basic Bloom filter supports only these two operations. Addition of object into that set. Okay, I haven't mentioned that Bloom filter can be viewed as a set collection. So you can add elements and you can test whether some element is a member of that set. That's all. It doesn't support deletion. It doesn't support iteration over the elements. You will see why. It provides very strong memory reduction because elements are not stored at all. Even if you provide there a reference to, for example, our structure object, that reference is not saved, and it doesn't prevent garbage collection to collect that input object. There are just few bits per every element needed compared to other standard collections which contains references. That strong memory reduction is compensated by some problems. One of the problem is false positive rate. Usually the default is 1%. That false positive means that if you ask for the presence of some object, it can falsely says you it is included, even though that object was not inserted at all into that structure. On the other hand, that false positive rate can be controlled. Default is 1%, but you can say 0.1 or 0.01% or whatever number you want, except 0. It cannot be defined that false positive rate is 0. It can be whatever number close to 0, but cannot be 0. On the other hand, it guarantees that there is no false negative. If that data structure on the test will say that element is not a member of that set, that 100% correct answer. So from this, you can find why it's called as a filter structure. Because for filtering, it is extremely perfect data structure. It can eliminate something because that elimination with false negative is correct. And I've already mentioned that it's not internally storing the elements, so the set cannot be iterated. Another benefit is that all methods, addition and tests or query, are always with constant complexity and really constant. It's not asymptotic only, or it's really always constant. The standard sets are not constant because there could be collisions with the linked list resolution. In this case, there is nothing like that. It's always constant. That makes this data structure very useful for working with the big data. And as I mentioned, because it's called as a filter, it's extremely suitable for filtering, for testing that some object is certainly not present in that set. For example, you can use this feature to reduce a lot of input-output operation or network communication if that element is not present. You can easily put there billions of objects inside this set because that size of that Bloom filter will be just a couple of megabytes. That size not increasing with every inserted object linearly, but different dependencies there. You will see that on the next slides. So that's extremely powerful data structure, which is used almost everywhere today to eliminate some more complex operations to happen, because it will say it's not there. And to say it's not there, you can even use false positive rate 1%. Because it says, okay, it's for 1% of cases, it will say it's there, and you will perform some more complex operations instead of not doing anything. But that's controllable. By this false positive rate, you will affect the size. You will see that on the next slides. You will affect the size of that data structure in relation to the number of elements. So if you would like to have it smaller, you have to admit bigger false positive rate and vice versa. So how it internally works? Internally, it uses bit array with m bits. So here we have our bit array. Then it uses k independent hash functions. So those are not linearly dependent of each other. In our example, we are using 3 different hash functions, g, f, and h. And how addition operation works with the constant complexity. If we are adding x element, we just simply compute k independent hash values for that x and use those hash values as an index into those bit arrays. And on every position, set true in that bit array. If we use that for y, again goes through those 3 independent hash functions, pointing to some different indexes in this bit array, and set 1 again on those positions. You can see that it can happen that for some different input, some of the hash functions could provide the same hash value, so there is a collision. But the probability is smaller if you are using multiple independent hash functions, that all of them will be matching together. So this one was or true was already set by x, but for y it's not modified. And the test operation or query operation works very similar. Compute those hash values and check whether there is true on every position where those hash values are pointing as indexes to that bit array. If there is everywhere 1, returns true. Element is member of that function. If one of them is 0, returns false. From this internal structure, you can see where the false positive rate comes from. Collisions of the values, right? So if you put there many elements, it can easily happen that for some there will be already 1, 1, 1, even though that element was not inserted. But it doesn't matter. It's mathematically proven how big that bit array needs to be to provide a rate inside that false positive rate. And that's on this slide. Number of bits on the filter can be exactly computed using this equation, where the n is number of elements you are willing to insert, and p is the probability between 0 and 1 for the false positive rate. So using these logarithms, you can compute number of bits needed for your array, for your Bloom filter structure. Same way, there could be computed number of hash functions which are needed to provide that. So you already know the m bits, number of elements you are willing to insert, so number of hash functions is computed exactly as well. Or you can use this chart where this is the number of elements. Here you can define the probability. 1% is 0.01 because this is in between 0 and 1. So if one example, let's have a set where we are willing to store 1 million of strings, where those strings contains in total 25 megabytes of data. If you are using a standard Java collection, set string, and insert that 1 million of strings, that collection requires more than 50 megabytes of size in the return size. If you use Bloom filter with false positive 1%, it requires just slightly over 1 megabyte of memory. By the way, that Bloom filter requires 7 hash functions, which can be found in this chart. 1 million is here, probability is here, you need compute, you need find the crossing of those 2 points, and here identify the number of bits, and also finally compute number of hash functions. So in fact, in our example, that Bloom filter structure is more than 44 times smaller and provides 99% true positive rate for the querying. So, for example, what can be used for this simple example? Dictionary or correction of the text. That usually works. The simple corrector usually check existence of the word. So if you do some typo, that word is not existing, and you need to quickly check that that word is not existing. In fact, you don't need feature for iteration over all known words. You don't need that. You need just true, false. It's correctly written or incorrectly written. And you allow some small false positive rate. It could be less than 1% to work perfectly. And as you can see, we are inserting million of strings. We can put there 10 millions, whatever number. So it's extremely efficient data structure. So that was the basic Bloom filter. There exist also many extensions. I will just provide you 2 of them so that you know that there exist and they provide additional features. So first extension is counting Bloom filter. Counting Bloom filter supports deletion and also estimate of the number of elements. How it works? Instead of having bit array, instead of bit on every element, you can have several bits. It could be, theoretically, it could be the whole byte, but it's not needed. Usually 3 bits, 4 bits, depending on the configuration. And then addition does just the set to true, but rather increment that value. Deletion is then decrement. And for sure, you have to test the bounds. It cannot be incremented so that overflow of the bits number is happening, and also underflow cannot happen into negative number or into the maximum if we are using unsigned, which is usually the case. Test, then just check that the value is non-zero instead of true-false. So depending on the size of the bucket of each position, the false positive rate and number of elements, which increase the probability of conflicts in the data structures, it can work well, and that bucket overflow problem can occur rarely. But it exists there. So you need to think, when you use this Bloom filter extension, that it could involve even false negative errors, non-zero false negatives, because it can happen that we are inserting, reaching the maximum value in the bucket, then we are removing, we cannot go underflow below 0, so we stand on the 0, then the test says it's not there, but in fact element is still there. So that's one extension. Another extension is Bitfees Bloom filter. It's slightly similar concept, but in this case, the number of bits in each element is predefined in advance. When you construct that data structure, it's already predefined. It will be 3 bits. That's it. Bitfees Bloom filter can dynamically react to the number of elements and conflicts, because it can be basic counting filter, and when it finds, okay, I'm willing to insert another element which will cause overflow of the counter. So instead of not doing anything, let's create parallel data structure and count in that. So there are, in fact, multiple counting Bloom filters dynamically added when we are inserting elements which cause conflicts. And also vice versa. If we are deleting elements and we are going to 0 in some data structure and everything is 0, we can eliminate that data structure. So it solves a problem with false negative, but it increases the requirements on the memory, depending on the collisions. So those are 2 examples of extension for the Bloom filter structure from the basic Bloom filter. But there exists much more. You don't need to create code for this Bloom filter structure yourself, because there exists a lot of frameworks, and usually you will not create good choice of the hash function constructions to have independent hash functions. So rather to go and use existing frameworks, because they are really tuned and proven to work as they should. So let's move to the last part of this lecture. And that's related to the reference objects. Up to now, I was talking about reference or ordinary object pointers, which is called as a strong reference. If that reference exists, object cannot be reclaimed by garbage collector. But there is much more flexibility in Java virtual machine with respect to references. Aside of strong reference, there exists soft reference, weak reference, final reference, and phantom reference. Final reference is in curly brackets. Why? Because it is not used explicitly, but it is used implicitly when you have finalizable objects. I will talk about that later. Difference between strong reference and any other type of the reference is that strong reference itself is just the pointer or ordinary object pointer. On the other hand, soft, weak, phantom references or final reference is a special object of that type which contains a strong reference to the referent. That's the pointer. So the type of the reference is determined by the type of that reference object here of the class. There are more features provided. It's not just the reference. There could be, for every reference object, there could be designated reference queue where the pointer to this reference object will be enqueued if something happens with the object here. It is important to say that enqueuing pointer to this reference object into reference queue happens only if you have a strong reference to this reference object. If there is no more strong reference to this object can be garbage collected in the next cycle, and then this can be garbage collected as well without any further action. And I've already mentioned that it's another instance. So in case of standard ordinary object pointers, the cost for this additional object is 48 bytes. Here you have one line example how, for example, weak reference is created. So just call the constructor of weak reference. Here you provide the reference to the referent as a first input argument, and this is optional. In this case, that's the reference queue. It's not mandatory for all types. For some, yes, for not all. So if we have various types of references, then we need to define a reachability level of the object. Because object can be strongly reachable, softly, weakly reachable, eligible for finalization, phantomly reachable, or unreachable. The strongness property of that reachability goes from top to bottom in this arrow. The same info is within this diagram where you see the transition of the reachability level for the object through various cases if there are multiple types of references pointing to them. So let's talk about each type of the reference, what is suitable for and how it works. So let's start with the basic one, which is the weak reference. Weak reference in this red is simply the meaning of the weak reference. Do not retain the referent, the pointer from this weak reference, just because of this reference. If there is another strong reference to the same object, fine, keep it. But if there is only weak reference to that object, garbage collection can take it immediately during the next cycle. Simply you are saying, by this weak reference, I am not owning the target. It's suitable for some cases like object output stream, where there is internally deduplication of the hierarchy of the object, because there could be cycles, etc., etc. So internally it uses weak references to do that. This weak reference also allows you to create a flexible version of finalization. You can prioritize finalization of various objects. You can decide when to run finalization. And also there is additional benefits like do not keep all object content if it is not needed. I will provide you example later. Weak reference itself provides a getter, and that getter returns the referent if it was not cleared before. If it was cleared, it's a null. So anytime you would like to work with such reference, you need first use the getter, store that returned value into local variable. In fact, then you are creating a strong reference. Then check that local variable which you just stored from that get is not null. And if it is not null, use that. It's not sufficient to do condition on get directly. And if that pass, do another get. Because in between those two gets, it can be cleared to null. Why? A referent itself is cleared by garbage collection cycle when there is no strong reference or different type of reference preventing its collection. So, and if it is cleared, then usually the object where it was pointing is reclaimed completely. So null is set by garbage collection. There exists this weak hash map typed by key value, where the weak reference is used for keys. So you can insert multiple values there under those keys. And if there is no more strong references to those keys, next garbage collection cycle reclaim those keys. And it means values will be removed from this hash map structure automatically. That cleanup of internal map.entry, as introduced last time, happens inside further operation with this hash map. Whether you are going to insert, remove something, it's cleared then. The cleanup, there exists in fact two approaches. One I've introduced in this weak hash map, that it's part of further operations on that object. In order to not to block calling thread, usually limited cleanup process is in place up to 10 elements or whatever. Do not clean up 1 million because it will consume a lot of time of the caller thread. And also use pooling for non-blocking fetch of the first from that queue. The other approach is to use dedicated thread. So let's create another thread which just use a reference queue and then in a cycle tries to remove the first element if there is such, and then dispose the content of the object and do it in the cycle. That's in fact something which happens for the finalizer thread. Finalizer thread is a dedicated thread for cleaning all finalizable objects. I will talk about that later. But now, introduce our custom finalizer, which is providing a benefit for managing priority and also other stuff. So let's define our custom finalizer class, which is extending weak reference. Here we have static fields, so just single instance. One of them is a reference queue. You can see here it is created. And then because that reference queue is working only if there exists at least one strong reference to the reference object, we need to keep strong references to all objects. And that we can do by this bidirectional list. And then have this circular end of the list inside this class in the static field. So by this, we can keep at least one strong reference to this custom finalizer instance. Then we have these constructors. We have these methods. This green area in curly bracket will be introduced on the next slide. And also, this class is defined as abstract. It cannot be constructed directly. because there is this abstract method, custom finalize. Normally, every object in Java is descendant of the object, and the object contains finalize method. That finalize method inside object is so-called trivial. It means it's empty. You can override that. But if you override that, it will cause and implies finalize reference creation automatically with a lot of issues. So you can use this custom finalizer to overcome these issues. And in this case, we define custom finalize. And we are not using the standard finalize. This static initialization block introduces dedicated thread for cleanup. Cleanup thread, the content which is executed is here, infinite loop, simply remove elements from the reference queue and execute custom finalize method. And do that until end. So that thread is configured as daemon, so not preventing termination of Java virtual machine in case of the termination of all other non-daemon threads, and start the thread. So this thread is calling our custom finalize. So let's look to the details. Constructor. We need call super constructor, just provide referent and reference queue, which was not needed in our own constructor because it's our own dedicated reference queue object. Then we are managing our double linked list with circular end here. Execute custom finalize, which is called from that cleanup thread. Simply check, is this not already cleaned object? If it is already cleaned, do nothing. If it was not cleaned object, let's remove it from double linked list and call our abstract method custom finalize here. In order to use this, you simply define this anonymous implementation of custom finalizer. You would like to monitor this provided object as an argument. And in case that object disappears from your application for whatever reason, our custom finalize will be executed. And that's it. There is the second benefit compared to the standard finalization, except those prioritization, multiple threads, and managing the priority of the object. Here, our monitored object, as defined before, is reclaimed by garbage collection in the first garbage collection cycle. It already disappears with all its references and descending objects. Just the custom finalizer remains. So this code uses just the limited subset of fields which are needed to perform cleanup. For example, if you are creating a graphic interface, usually you need to work with the graphic card through the APIs, and on every object on the graphic card receives some handle, and those handles needs to be destroyed as well. If you destroy some image, it needs to be destroyed on graphic card. But you don't need to keep all information from that image, was, were, etc., etc. You need just keep that handle ID, and that's the part which will be included inside our custom finalizer only. Just use that handle to call destroy object on the graphic card, and that's it. Everything else can be destroyed during the first garbage collection cycle, not the later. That is something which is not possible with the standard finalization. Standard finalization of the object keeps all the content of the objects until finalizer thread calls the finalize method, and also further garbage collection cycle happens. Then the object is cleared. So let's move to the next type of the reference, soft reference. Again, in the red is the meaning of the purpose of the soft reference. I would like to keep the object, but can lose it. So it's suitable for caching. If there is no memory pressure, let's keep that object in memory. If there is not enough memory, let's remove these objects. And during the removal, use LRU mechanism, least recently used mechanism. So objects which are used most recently are kept, but the older objects which are no longer used are removed automatically. So there is this mechanism using timestamps. This is constant, which can be modified at the startup. By default, this constant is 1000. And it works with the amount of free memory in megabytes from the last garbage collection cycle. So, for example, if we have 2 GB of free heap, if it is in megabytes, it's 2000. And with this default, timestamps are in milliseconds. So if you convert everything back correctly, you get time in seconds more than 2000 seconds. It's slightly over 30 minutes. So in fact, object will remain in the memory for 30 minutes if there is at least 2 GB free memory. Before, our application throws out of memory error during allocation of new objects, all soft references are cleared. So we are running out of memory, and so in such case, we are removing almost all objects softly referenced because we are getting with the free memory closer to 0, so this time difference is closer to 0 as well. Similarly to weak reference, get returns referent if it is not cleared. And plus, it updates the timestamp of the last usage. Anytime you call get, it internally remembers the timestamp when it was used last time. Same to the weak reference. Referent is cleared by garbage collection immediately, and it can be reclaimed before the soft reference object is removed. Again, same to the weak reference. Reference queue is optional. Can be used, but doesn't need to be used. It's up to your case. So let's look to one example, creating some efficient cache mechanism using our LRU approach, least recently used approach, in combination with memory pressure, but cache which guarantees that some minimum amount of elements are preserved for sure. We cannot use directly only weak hash map because we would like to cache the values, not the keys. Weak hash map consider as a weak only the key, not the value. So in our case, we are utilizing this weak hash map, but as a content, as a value, we are putting there a soft reference to some value holder. Value holder contains a strong reference to the key that prevents that even there is no external reference to the key, our key pair is not removed from the weak reference because there exists this strong reference to the key. And also there is a pointer to the cache object here. That's one thing. Another thing is this fixed value holder array, which works as a strong reference to the value holder for the last usages. So anytime we are using some value from that data structure, we are simply storing a strong reference to this fixed value holder array, which prevents garbage collection of the value holder and thus prevent garbage collection of the key pair in the weak hash map, and also for sure because there is a strong reference to the cache object that is not cleared as well. This is very simpler approach because we can use fixed array and just rotate the pointer. Every time we are getting some value, we increment the pointer and override one of the value, and we are going in cycle. So it's cycle structure for the array just to keep for sure some minimum amount of elements. Elements which are not recently used are not pointed in this structure, And then there is LRU mechanism applied directly as a soft reference to them. So if there is a memory pressure, value holder is removed. That immediately removes the cached object, removes the strong reference to the key. There is no more reference to the key, so weak hash map is cleaned, so this record is removed automatically during the garbage collection cycle, and that's it. So that's one approach how you can do efficient caching. There is also existing a lot of frameworks like Spring providing caching, and they have implemented this approach inside already. So you don't need to write it yourself. So let's move to the next reference type, which is a final reference. It cannot be used explicitly. It is used implicitly by overriding finalize method, as I've already mentioned. If you override finalize method and then you do new of such object, the allocation is much slower than for the standard object, because every time when new object is allocated, it calls this factory matter finalizer register, which implies global save point. Usually this finalizer register is not inlined. So if you have object with non-trivial finalize methods, those are not part of escape analysis at all. There are usually global escape, and that's one of the problems of such objects. It automatically allocates final reference in case of doing that creation inside this register and do all the stuff. The difference to the previous two types, weak reference and soft reference, is that the referent here is not cleared by the garbage collection during the first garbage collection, because the finalize method requires to still contain the data of that object instance. So simply all reference objects, and reference objects not directly but transitively via any number of different objects, cannot be reclaimed during garbage collection cycle at all as well. That's the major drawback compared to custom finalizer, where we don't have this problem. And if you have big data structures somewhere, those are immediately removed from the memory, just our custom finalizer reminds. In this case, object, fully the object and everything inside is kept. Another drawback is that there is just single one finalizer thread performing call of finalize for every object which are ready to be removed from the memory. So in fact, you can view that there is a first garbage collection cycle. There are no more references to that object. Then it enqueues finalize reference into finalize reference queue. After some time, our single finalizer thread processing that final reference queue is taking our object, calls the finalize, and complete that finalize. Then another garbage collection cycle knows, okay, this object was already finalized, and we can reclaim the space. There is even more problems, because during the finalize call, you can technically create another strong reference to that object which is being finalized. And that's the problematic case, because it means it cannot be cleared even during the next garbage collection cycle. And I've already mentioned this subsequent garbage collection cycles. So that is the final reference. The last type is a phantom reference. This is post-finalization processing, so after object is finalized, if it is suitable for finalization. And its usage is like it can be used as a notifier that the object is really not used anywhere. So if you would like to really track somehow existence of object, you can use that phantom reference for that. Another use case is if I have multiple objects which implements finalization or custom finalization, I can imply order of the finalization. In case of our example with graphic interface, if you create some 3D scenes, usually you provide textures, various additional attributes. There could be multiple textures assigned to some complex object. And that assignment is then done via referencing those handles. So you cannot destroy the textures before object is destroyed. So you need a dependency of the finalization. So here is our example. Global table stands for some local variable, for example, or static variable or whatever. So this is strong reference, these two arrows. Then we have our two objects, A and B. Both are finalizable in this case. And we would like to guarantee the order that A is finalized first because it's an object using something else. And once it is not existing, we can finalize B. How to implement that? For example, using phantom references. Those are this object with apostrophes, A apostrophe, B apostrophe. This is a referent pointer. So they are phantomly reachable, these objects. But there is also, because you can use phantom reference like example of the weak reference, you can extend that class. So there is extension providing a strong reference to the B object. And this strong reference simply guarantees that there is at least one strong reference to B, so it cannot be finalized until A is completely destroyed. After A is destroyed and there is no more this strong reference, then this can be finalized and destroyed as well. So by phantom references, you can create these dependency chains. The getter is working slightly different. It always returns null. Technically, a referent can be read because there is a field inside a referent using a reflection, because Java language allows you reflectively read values for whatever field. That's possible. You should, but it's not ensured inside the runtime, avoid making strong references again to something which is being phantomly destroyed at the moment. But technically it's possible. This is the only reference type which requires as a mandatory reference queue. Why? Because getter always returns null. So it's used only for tracking. So to summarize that, if you have objects which are only strongly reachable, or there are soft and weak references to those same objects only single one garbage collection cycle is required to reclaim the content of the object. Those could be reclaimed. But if it is finalizable, it cannot be reclaimed, because that first garbage collection cycle just identify, yeah, it's finalizable. So enqueue into finalizer queue, then the finalizer thread needs to process that, and after processing, subsequent garbage collection cycle can clean the object. This very same happens also for phantom references, because phantom are very last, and if it is finalizable, it even requires 3 garbage collection cycle. If there is no finalization, at least 2 are needed, because within this first garbage collection, they become phantomly reachable, so that phantom reference is enqueued, and after processing of phantom reference, object can be reclaimed. So that's the drawback of using finalization, non-trivial finalize method, and more complex reference object. But with this concept, you can do a lot of interesting stuff inside your application. And sometimes it's really needed. You don't need to own the target, as I've last time mentioned, that sometimes anonymously created listeners automatically contains references, strong references to enclosing classes, and prevents their collection. If the framework which works with those listeners say, I don't want to own that listener and store them into weak references, that doesn't occur. So that has to be implemented properly. So if we summarize cost for references, there is a for sure creation cost, because except of strong reference, all additional references are additional instances, 48 bytes. There is needed synchronization when working with the reference queues. So if you are using just soft references and weak references, though have optional reference queues, so not needed, then there is no cost for synchronization. Garbage collection itself implies additional cost, because you can imagine that if you have a graph of objects, complex graph of objects, and there are also different types of references, not just the strong references, all has to be properly tracked. And you have to identify what type of reachability you have for every object. So there is a cost inside garbage collection itself to do traversal, enqueuing of the object into reference queue. Then also the reference object itself is another pressure for the garbage collection. And also outside of that garbage collection cost, there is for sure, if you are using reference queues, there is a cost for the processing of those reference queues. Usually that requires synchronization to work, because newly created is added, and if you process it, whether using a dedicated thread or parasite on some additional operation, you need synchronized operations on that. So if we talk about reachability of object, this is what garbage collection needs to do. So let's have an example with 4 types of references. We are not including final references, but they are working exactly the same. And define different types of reference. Strong is gray, yellow is soft, blue is weak, and red is phantom. Here we have 6 cases. So in the case 1, we have one object where we have just the strong reference. So in case 1, it's easy, strongly reachable. In case 2, we have 2 references. One is strong and one is soft to the same object. So what is the reachability level of the object in the case 2? Do you know? Correct. It's strongly reachable. Why? Because you need maximize. If there are multiple incoming references, as defined on some earlier slide, the reachability level is higher on the strong references. So the maximum reachability of this object is maximum type of that reachability level here, which is the strongly reachable. Adequate case 3. In this case, we don't have strong, we have just the phantom and the weak. Again, 2 incoming references, simple, maximum from those 2 incoming is weakly reachable. Because phantom is processed after it's not weakly, softly, or final, or it's already finalized. Then we have down here another 3 examples. So, changing the case, we have strong reference to the weak reference, and then weak reference to the object. What is the reachability level of the object? Correct. It's weakly reachable, because in case of serial various type of references, it's a minimum on the whole path from the root. And the minimum here is weak. So object in case 4 is weakly reachable. Here is just the analog case where we have one more reference type in the chain. So we have phantom reference to the weak reference to the soft reference, and soft reference to the object. So in the case 5, the minimum over the whole path is phantom. So the object is phantomly reachable from the beginning, because all this is already phantomly reachable and it cannot increase the reachability level. Case 6 is most complex, because here this dot line in the middle is the root references. So it means that in fact we have here a strong references to the soft reference and to the phantom reference. And then we have reference to the weak reference. From weak, we are pointing back to the soft reference, and both soft and weak points to the object. What is the reachability level in this case 6 for the object? Soft, correct. Softly reachable. Why? Because we have to first study the reachability level for every path. So the minimum here is phantom for the left arrow. What is the minimum going here? Here we have strong, so we doesn't need to count this. So this is softly reachable. So we have two incoming references. We have phantom and soft. If we have multiple, we are maximizing. What is the maximum? Soft. So the reachability is soft. All this determination is done inside every garbage collection cycle, and that causes some internal overhead, because depending on the reachability level, then the garbage collection needs to decide, oh, okay, it's softly reachable. What is the last recently used time for that object? Do we need consider cleaning right now or later? So all these decision processes cost runtime time of your application. Okay, and that was the very last slide I have today. So thank you for your attention.